Hey guys, Sigma here. I'm going to be going over some math notation with you guys. I'm not going to be going over like some really simple stuff like, uh, like dots and multiplying, but I am going to be going over the uh, like large operators and, uh, and a few other like written out expressions that are really interesting to see what happens when you do that. Some people may be familiar with them. Um, with that one, people who do like computer science and stuff, they'll definitely be uh, knowledgeable in that stuff. Um, Engineers such as myself, definitely kind of would know that in a sense. But yeah, so without any further ado, let's get started. It's so satisfying every time. All right, so the first one, I might as well get it out there. Um, the Greek letter sigma, right? So sigma is a large operator that works by summing, right? Actually, I'm gonna write this right here. This is used for, well, you say it out. It's just like, okay, we're gonna use the sigma summation notation, or sigma sum notation, um, right? Up here is the upper limit, right? So the upper limit is generally denoted with an n, where n equals some number or something, and the lower limit, right, denotes, well, generally with a j here, denotes the increments on how you're going to get here. You're going to go from here to here, right? So you're counting up in increments. And this is like with these limits and stuff. If you find the limit, of a sum or the limit of a series, or something, um, as let's say n goes to infinity or something like that, and you have some function delta xj, whatever, you're basically just finding the integral for the area, Uh, but the point is here is that, actually, let me give you guys a good example, right? Let's say for whatever reason we had two. We just have let's just place a whole number here, right? Right, let's say j equals 1, right? And we're going to count, let's say we want to do this n number of times, right? So let's do this 3 times, right? A summation, right, is just sum. You're just adding it all together. So I'm going to add 2 3 times, right? If that's how you did it, that's you only partially right, right? See, what really happens here is I need to count from j to n by using j increments, right? So with the way this works, so if j, this is generally right here, it's for, let's say I have to the n power. Let's not worry about that right now. Right now, right, we're just getting the basics down. J has to count to n. Right. So as j increments, we have a whole number. There's no variables, so nothing changes inside. Nothing. No, there's no change in values. Um, so what ends up happening, right, is we have to add 2. It's 2 plus, okay, well, j is 1, so the first one is 2. That's where j equals 2. So that's still 2. J equals 3. Right? Oh, we finally counted to 3. Oops. Haha. Right? So now this is what I end up with right here. And as you'll see, right, all of this, right, is literally just 2 times 3. Right? So the summation notation is like, it's an alternate or more advanced form of multiplication. Right? You can use it, like I said before, with integrals, finding areas, usually in series, to find like convergence, divergence. Sometimes you can do it. Well, that's other stuff actually though too. But yeah. Well, and you can play around and do whatever you want, and just remember like that this is the first 2, this is the second 2, this is the third 2, and that just remember this is just go and say that this is the first what's inside the parentheses. Let's let's just give a quick example actually. All right, so I'm using j here as so we can see what happens as we increment. So what this reads is the sum of f of j where n equals 3 and j equals 1, right? And over here we have f of j is 2j, right? So when j equals 1, right, we have f of 1 because j equals 1, right? And then f of j, 2 times 1, right? So I have 2 times 1 plus, right? And then let's say, okay, now we have to increment again, right? So we're counting to 3, right? So j equals 2. So the second one, right? Remember, this is our first time through the loop. So j equals 2, j equals 2, j equals 2. So we have 2 times 2. And this was our second time through the loop. So the next one here, j equals 3. So let's just go ahead and write that in. We have 2 times 3. Right? So now we have our multiplication here, right? We kind of multiplied. We just kind of added a contingency to it, an extra condition, if you will. So let's go ahead and figure out what this is, what this all equals, right? So the first one we have 2, so we have just 2 plus 4 plus 6. Eesh. Eesh. That 6 is hurting. And then let's just, that's easily 12. So the whole thing is just equal to 12. So we can even rewrite this out, right? As, let's say, sum of f of j equals 1, n equals 3, where n is all equal to 12, right? And then, like those little notes at the top of your question, you're just like, where f of j is equal to 2j. Yeah. I mean, you could write that underneath, I guess, or above. Sometimes it's, honestly, who writes those questions? All right, but that's, so there's your summation notation, all right? All right, so the next one I'm gonna go over, right, is the pi product operator. So pi is another large operator. It's for multiplication instead of addition. So I think of it as repeated addition, repeated addition, repeated addition. Sigma was repeated addition, right? And essentially, I remember hearing this not too long ago, actually. You could actually think of multiplication as repeated addition, right? So, and and if you think about it, it makes sense. You're like, oh, yeah, well, duh, you know. And so for pi, right? This is going to be repeated multiplication. And what is repeated multiplication? I bet you already know the answer, and we're going to get there, right? So with this right here, we already have the same thing right here. Let's say j equals 1 and n equals 3, right? For this, we'll just say we have, we'll do the same thing again, right? We'll just say we have f of j, right? Let's say f of j is equal to 2j, right? So let's see what the difference is here. Last time we got 12, so let's see what we'll get this time, right? All right, so let's go ahead and work this out. We have here, let's see here, j equals 1, right? So we have 2 times 1. So we have 2 times 1. This is our first one here. And then our second one here, j equals 2. So we'll just replace that with a 2 right up here. So then instead of adding, we're going to be multiplying by 2 times 2. This is our second one. And then we're going to multiply again by the value of the function, which in this case here we have 2 times 3. And that's our third one there. Right. So this is basically the output of our product here. Right. So when we look at this, we have 2 times 4 times 6, right? And then here we get 8 times 6. And if you guys didn't already figure it out yet, the pi product, actually acts more like an exponential operator. It's more for, yeah, they're basically like exponents, So yeah, and then what we get here, let's see here, was that 48? So yeah. So let's take a look at that exponent part real quick. All right, so we're going to take a look at the product operator with just a base number, or just a whole number, I should say. So with the whole number 2, right? So we just have 2, right? And then j. Nothing really changes on the inside at all because we don't have a function. But we do have that whole number, so it's still there, right? And so you can already kind of tell what's happening. And then I increment again for the last time, right? And if we wanted to compact this down, right, you have 2 to the third power, right? So we're multiplying 2 n number of times, right? Alternatively, I have 2 to the n power, right? Because that you know that's what we got. We can also take a look back real quick at the summation notation, right? For the sum, right? If I had that 2, right? What would I get out of it, right? I'd have 2, let's say n equals 3. 2 times n, right? Because we're adding 2 n number of times, right? That repeated adding, right? That's the multiplication, right? Whereas over here, this was repeated multiplication already, so this turned into an exponent. Now, on the subject of exponents, which I know everybody loves, yeah, on the basis of exponents, we have something interesting. Let's take a look at something real quick. Let's make a quick observation, right? So this quick observation, right? If I have, let's say, base number 2, I raise that to some exponent, right? 2 to the third power, right? Over here, I'm just going to say I have my base number. I'm raising this to some exponent. What I get out of this, well, in this example, is going to be 8. Over here, we're going to call this our product. Right. Well, that's easy, Well, if I go over here and I'm going to say, well, what's the cube root of 8? Right? Well, what just happened here? Right? Basically, I have the same numbers, right? What I did is I took that exponent. I have the exponent root, right, of my product gives me my base number. You can probably kind of see where I got that, but I mean, and it's essentially root, right? So the last thing I'm going to do, right? So we have the base, the product. How do we get the exponent? I bet you already know. So the product, right? Let's say we want. Oh yeah, by the way, we got 2 right here. Right. So if we do log base 2 of our product 8. Right. So logarithms, right? So log base 2 of 8 gives me what? Right. You can kind of already see log your base product gives you, well, the only thing that I'm missing of these 3 is my exponent, right? So what this tells me is that whatever I had here, I'm raising it 2 to what power is 8, is long story short. 2 to the third power is 8. The reason why I wanted to get this out of the way is because I'm going to be using logarithms and exponents, and the next, it's more like a sentence. It's something interesting. Let me just go ahead and write it down. If you're unfamiliar with Newton's method on or at all, then it may be a little difficult actually, but To be honest with you, it's actually it's a pretty fairly easy concept to understand. So let me just go ahead and write this down. All right, so I got this right here. So check this out. This is a really interesting point, especially when it comes to large operators, right? So what we have here, this is all using base number. Our base number in this case is 2, right? Um, so it's just yeah. We have a large operator already, so we know we're going to be doing something with exponents, right? And we have our logarithm, so we're going to be doing something else with exponents. So what really happens here? Well, let's say we pick 2, right? Let's say we start off v of n right here is 2, right? So what I get right here, I have 2 to the second power, right? 2 to the second power. Well, okay, 2 squared is 4, right? Well, then that means over here is 4, right? Right. So, okay, well, what's this right here? Well, 4, what's 2 to the 4th power, right? 2 to the 4th power is 16, which means this was 16. Okay. Now, if we increment up 1, right? If we go up 1, because remember in the beginning that this was n, which is our current one, and if we go up 1, let's say we go n plus 1, or yeah, n plus 1, that means the 4 now goes, well, yeah, the 4 goes here now. So because the 4 goes here now, we don't have a 2, we have a 4. Okay, so 2 to the 4th power. Well, okay, this is 16 now. Well, this isn't 16. Well, what's 2 to the 16th power? I'm telling you what, that's a big number. Right? This is and this is a really interesting concept. This is one that's actually frequently used in computer science. What this is called is tetration. This is it's not necessarily repeated addition, repeated multiplication. It's repeated exponentiation. See, what we have here is the first time through we have 2 to the 2nd power. Then we go 2 to the 2nd power to the 2nd power. Then we have 2 to the 2nd power to the 2nd power to the 2nd power. And this goes on, right, n number of times. And you better believe it that those numbers get really big really fast. Right. And the reason why I say this is kind of a pain to write out a lot, because you can already see this is a lot. But the reason why it's really cool is you can see how these numbers, one moves to the next slot. The next slot moves to the next one, and the next one, and the next one, and they just keep going on and on and on. And it's just this own little engine, the way that it just, it just works. It just shows you how it goes. It's literally just this, right? It shows you how or what happens when you add that next exponent. Now, I'm sure just like any other large operator, right? You can add conditions to it, right? Like we do 1 over something, and and you can find the series and divergence, convergence. We can do a lot of stuff with it. It's really cool. It's really cool. Really interesting topics. Um, not a lot of people people ponder about this too sometimes. What do you do 2 to the second 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 to the second? Well, there's a thing for that. Also, it's a big number. All right, guys. Let me know what you guys think in the comments below. If you have any other suggestions for future topics, let me know. I'll see you the next time. Bye.